Okay, now this is the second part that we'll be looking at. So this is based on the stress strain graph. Okay, stress strain graph. Okay, so when you refer to stress strain graph, okay, so you have this axis here as this for the stress, and this is for the strain. Okay, the stress and the strain. So probably you all know what is stress and what is strain already, yeah? Okay, so this symbol here stands for stress, okay, and this symbol here stands for strain. So the graph here shows the line on the curve here, okay, representing a ductile material, a mild steel, okay, for mild steel. So the shape of this graph here changes if, let's say, for example, you refers to different materials. But for mild steel, the shape of the graph looks like that. Okay, the shape of the graph looks like this. So you have points here. Okay, these points here. What are these points here? So this is the point where your stress and your strain is 0. Okay, so when an object or when a rod or a bar is subjected to stress, okay, or subjected to load, as the load increase, the stress and the strain also will increase at the same time, because the strain is basically based on the deformation of the bar or the rod, and the stress is based on the force that is applied. So from this point to this point here, okay, you can say that, okay, the strain is directly proportional to the stress. Okay, so as you can see from this point to this line here appears to be a straight line. Okay, a straight line. So therefore, we say it's that the strain is directly proportional to the stress. Okay, so for this slope here, the slope here of this straight line, okay, the slope or the gradient of this straight line actually refers to the Young's modulus or the elastic modulus. So if you take any point on this straight line here, any point on this straight line here, not necessarily these 2 points, okay, not necessarily these 2 points, any point, any 2 points, okay, within this straight line here, when you measure the slope or when you find the slope, okay, of this straight line, it will give you a value that is called the Young's modulus. So I hope you all know how to find a slope from a straight line. So what you have to do is you have to take the vertical, okay, distance divided by the horizontal distance here, the vertical length. If let's say, for example, based on these 2 points, you can draw any 2 points within this line here. Not necessarily these 2 points, I repeat, okay? Not necessarily these 2 points. So let's say, for example, you draw a straight vertical line down and a horizontal line across. So what you have is, okay, to find the slope, you have to take the length of this vertical line divided by the length of this horizontal line. Okay, so when you take this value divided by this value, you get what we call the Young's modulus. Young's modulus or the elastic modulus, and usually is denoted by a symbol of E, uppercase letter E. Okay, so any object that is stressed or any rod or any bar that is subjected to this, okay, we say that the material is elastic. What it means by elastic? Elastic means when you apply force or load onto the material or the object, okay, what happens is it will undergo elongation. But then when you remove the load, the object must be able to restore or to spring back to restore to its original length. Okay, then only we can say that the material is elastic and it obeys Hooke's law. Hooke's law says that, okay, stress or strain is directly proportional to the stress. So that gives you the slope of this line. So within these 2 points, we say that the material is elastic. Okay, and at this point here, the object will go under strain hardening. Okay, and then further on at this point to this point here, if the object is stressed or is loaded or is forced or is stressed beyond this point, what happens is it will undergoes a change, a slight changes in the line, and then it appears to be a curve until it comes to the last point here where the things will start to break or to rupture. So this section here, we say the object or the bar will undergo necking. So at this point here, we call it as the elastic limit. Okay, and this point is the ultimate stress. This is the ultimate stress. And from this point here is called the rupture stress. Okay, the ultimate stress from this point, you draw a straight horizontal line across, okay, touches the stress axis. So we'll give you a value which is the ultimate stress. Remember, okay, for any calculation work or any design work, we are not advised to use this value here straight away. Okay, we usually use ultimate stress divided by a factor of safety in order to get the allowable stress. Okay, so and then here that is your rupture stress. That is a stress when the object starts to or the material starts to break. And at this top here, this notch here, okay, this tip here will give you the upper yield stress, will give you the yield stress. And then when you compare, this is higher and this is lower, so we call this as upper and this as lower yield stress. Okay, so the upper yield stress and this point here will give you the lower yield stress. Okay, that's the stress against strain graph in general. So remember, the most important thing is we know that this part here is the Young's modulus, the slope of this graph. Okay, now this E value here, the Young's modulus, okay, will be known as, or it is known as a material constant. So that means, okay, this E value here, the value will remains the same, okay, even though you apply different forces or when this material is subjected to a certain amount or a different amount of changes or deformation until it touches this point. So the E is a constant for a particular material. So let's say, for example, the E for mild steel, because this curve here, this graph here refers to mild steel. So the E value for mild steel is roughly around 200 to 220 gigapascal. That means giganewton per meter square. So this E value will remains the same, that is 200 to 220, either 200 or 210 or 220. Okay, even though you have a force of 10 kilonewton, 20 kilonewton, 30 kilonewton, or 40 kilonewton force, or stress of, let's say, okay, 10 megapascal or 20 megapascal or 30 megapascal, and it won't change with respect to any stress value or any deformations that occur within these 2 points. So that is why it's called the material constant. So E value for mild steel is from the range of 200 to 220, then it might be different. It will be different for other material, let's say copper, aluminum, and so. So the E value, there is a standard E value, okay, for each material. Remember, they are called material constants. The E is called a material constant. So for different materials, okay, the E will be different. If it is the same material, let's say it's only mild steel, then the E you can consider as a constant. Let's say if you are using 210, then it will be 210 throughout, whatever stress or strain that might occur within these 2 points. Okay. So here we have a diagram showing you how this material or how this rod here is deformed. So usually it is being done experimentally. So in our college we have, okay, this machine which is called the tensile testing machine. Okay, so what we do is on this specimen here, usually we mark down 2 points, okay, and this force here, the tensile force, when you remove the tensile force, what happens is the material will spring back to its original length, will give you the same distance between these 2 points. Then we say the material is elastic. That means we refer to this point here. But if let's say, for example, this material here is further stressed, that means you increase the force, okay? So what happens is after this point here, the material will start to deform, okay? Partially, or we say partial elastic or plastic, okay? When we say partially elastic, that means when the force, after the force, the removal of force, the length of this object here will only return at a certain percentage back to its length. That means to its natural form. Okay, only a certain percentage. That means will not fully spring back. Okay, at this point and this point here. And then if it further, okay, the load is further increased or the stress is further increased, what happens is it will enter this region here, which it start to form a neck. This is called necking, a neck. So before it breaks, this one, it shows that it is breaking already. Okay, so it will undergo plastic deformation here. And then further stress beyond that, what happens is it will form necking. Then if let's say more force or more stress is being applied to the material, what happens is the thing will break. Okay, the thing will break into 2 parts. Okay, so what happens is when you look at the diameter of the specimen now is slightly, or it is lesser than the original diameter of the specimen. The final diameter of the specimen now becomes smaller than the original diameter. So that is the cause of necking when it is stressed beyond, when the material is stressed beyond these points here. Okay, so until it reaches this, then the material will break. Okay, so the diameter of this, the original diameter, will give you the original cross-sectional area. And this will give you the final cross-sectional area based on this diameter here. So what happened is, okay, you will have a change in cross-sectional area, and that will cause the failure. Now, we're back to the stress strain graph. Now, first thing is elastic limit. So I have the definition for elastic limit here. So whenever some external system of forces acts on a body, okay, act on the body, it undergoes some deformation, a certain amount of deformation. Deformation means elongation, extension, increase in length, okay, or contraction or compression. In this case here, we are referring to tensile test. So therefore, the deformation here will be referring to elongation, extension, or increase in length. And if the external forces are removed, that is based on elastic, okay, elastic, the material is being elastic, yeah. So elastic limit is here. And if the external forces are removed, the body must restore, if it is elastic, to its original sizes and dimensions. Now the body is said to be stressed within, that means inside this range here, That means inside of these 2 points, that means within these 2 points. Okay, so we can call it as elastic, and the point is called the elastic limit. So this is the elastic limit. So beyond this limit, that means beyond here, or beyond this, okay, the body is said to be plastic. So it undergoes plastic deformation, or it is semi-elastic. So plastic deformation, okay, what happens when the specimen undergoes plastic deformation? So it will be permanently deformed. It will not return to its original, or it will not restore to its original sizes or dimensions. That is due to plastic deformation. Semi-elastic means, okay, the object will only return partially, not fully, okay, back, okay, to the specimen itself. Okay, yield point. These two are the yield points. Okay, so a slight drop or increase in the force when it reaches these 2 points, or when it goes beyond this point here. Okay, when there is a slight drop, that means a slight decrease in the force that is applied, or the load that is applied, or a slight increase or a slight decrease, what happens is it will result in a very large amount of deformation. It's not the same as these two, within these 2 points here, any points within these 2 points here. Okay, it's not the same. Okay, what happened here is how much you stress, how much is strain. So the percentage stress will be equals to the percentage that is deformed, that is proportional. But then after this point, it will not be proportionate anymore. So a slight decrease or a slight increase, slight decrease or slight increase of force or load, what happens is it will result in a very large, okay, a significant changes in length. Okay, a significant, that means a large amount of difference when you look at the length. That is when it reaches the yield point here. Now, maximum and ultimate stress, that means at this point here, we call ultimate. Okay, that is the maximum stress or load that the material can withstand before necking takes place. This is the maximum stress or the maximum load that the specimen, this specimen here, let's say this is a mild steel specimen. This is the maximum stress. Maybe it's maybe it is a certain amount of 400 something megapascal. Okay, it's 400 something megapascal, 300 something to 400 something megapascal. So when it reaches that point, okay, we call that as the ultimate stress that the material or the specimen can withstand. So after that, what happens is necking will start to take place. So you can see when the slight increase in force or stress to the specimen here, after this point, it will undergo a very significant uh, reduction in cross-sectional area around the middle portion within these 2 points. So that is called necking. Okay, that is your ultimate stress. Okay, so remember the slope between these 2 points, that is C and D, the slope here is equals to what we call Young's modulus or elastic modulus. And you can measure or you can determine or find the E value by taking the vertical length divided by the horizontal length based on any point within C and D. Okay, so when you take the vertical length divided by the horizontal length, you get the stress, the average stress between here, between these 2 points here, the average stress and the average strain. Okay, strain, that is horizontal. The stress is the vertical value, yeah? So you get this value here, which we call the Young's modulus. Now, for ductile materials, okay, you can see, you can notify that there is a slight, okay, curve of some sort like that forming on the graph. But for brittle materials, you won't see this. Okay, you won't see this, and especially why mild steel is taken an example for our studies or for most of the studies of stress strain graph. Because for mild steel, which is a ductile material, it can show you a very clear something like this form on the curve. Okay, follow? So this graph here actually refers to mild steel. So note, many materials do not have well-defined yield points. That means not many materials have a defined yield points like that. Okay, not many materials. This is particularly for mild steel. You can see something like that. Okay, many materials do not have well-defined yield points. The stress strain graph being more like that shown in the figure beside. In such instances, a proof, if let's say, for example, material that doesn't show a well-defined yield point, then you have to use something which we call proof stress. Proof stress. Let's say, for example, if you are given 0.2% proof stress, that is defined as the stress which results in a 0.2% offset. Okay, I will show you afterward. Example, the stress given by a line drawn parallel to the linear part of the stress strain graph passing through 0.2% of the strain value. So look at this graph here. So this is the stress strain graph. Now for mild steel, you don't need to use proof stress, okay? You don't need to use proof stress for mild steel or for most ductile materials, okay? Now, let's say you have a graph like that, okay? This is not mild steel anymore because it doesn't show you a proper, the proper upper yield and the lower yield, okay? The curve. It doesn't well define the curve for yield and upper yield and lower yield. So this, for this example here, which you don't have this well-defined yield point, okay, you need to use the proof stress, okay, method. So what you need to do is, so let's say, for example, they say 0.2%. So what you have to do is based on this, okay, you have to take 0.2%. So you have to measure 2/100 of the original length. Okay, so from that point, you draw a line parallel to this line here. From this point, you need to draw a line shown as dashed line here, parallel to what I have drawn here, until it touches with the red line. Okay, until it touches with the red line, and then you draw from that point, you draw a horizontal line across. Okay, so what you have here is known as the proof stress. Okay, so that is the 0.2% proof stress. That means referring or respect to this 0.2% strain. So then you can find out the stress. Okay, if let's say, for example, you have material that doesn't, when you do an experiment, let's say, for example, materials not as mild steel, okay, and then you cannot get a proper curve as what I have shown you, a proper defined viewpoint, then you have to use this method to find out what is the proof stress. Okay, so or you refers to a load extension diagram. This is stress against strain. This is force kilonewton against extension mm. So what you have is the same curve here. Now, when you say 0.2%, that means you take 0.2% of the original length. So you take original length, let's say is 100 mm. Original length, let's say is 100 mm. So you have 0.2 over 100 times 100. So what you have is actually 0.2. So therefore, from here, okay, you have a 0.2% of original length. So that means it's 0.2 lah. Okay, so from that point, draw a line until it touches this. You got a point, and then you draw across. Then you got this as proof load. Proof load. So if you take this force divided by the area, you actually must get this amount of stress. Okay, theoretically. Okay. Now, then the next part is what is factor of safety. Now, structural members or machine must be designed such that working stresses are less than the ultimate strength of the material. Now, remember what we have in the graph just now. When you say ultimate stress, that means that is the value of the maximum stress that, or the maximum force or maximum load that the material can withstand. So, for example, when you refers to mild steel, you have only one value of ultimate strength or ultimate stress, only one value, let's say 400. Okay, so you cannot use this 400 straight away to do any calculation work or any design work. So what happened is this ultimate strength, you must divide it by a factor of safety in order for you to find out what you call an allowable stress. That means the stress that is safe, okay, to be used for the purpose of design. So Fs stands for the symbol of factor of safety. Usually, factor of safety is defined as the ultimate stress divided by the allowable stress. So for allowable stress, if you want to find allowable stress, because you need to know, okay, what is the working stress? So you have to take the ultimate stress divided by factor of safety. Ultimate stress divided by factor of safety will give you the allowable stress. Now, how do we consider the factor of safety? Now, there are different values that varies from 1 to 10 or more than that. Okay, now the value of 1 to 10, it depends on the applications of the material, okay, or the type of material. So I have a list of things that you should look at, okay, for considering what is the safe or what is the proper value for the factor of safety for various design. So factor of safety is considered when there is an uncertainty in material properties. 2, when you have an uncertainty of loadings, okay, the loading type, okay. Now, later on, we will go to loading types, okay. Then uncertainty of the analysis, okay. Then number of loading cycles, types of failure that might occur, maintenance requirements and deterioration effects, importance of member to integrity of the whole structure, risk to life and property, risk to our life, yeah, influence on machine functions. So these are the various points that we have to consider in order to look into what is a proper value of factor of safety. I can tell you, if you use smaller value of factor of safety, you find out that the material that you can use is wider in range. Wider in range, that means you can choose a lot of different materials. Okay, maybe you can choose cheaper materials for your design. But when you refers to a higher factor of safety, the limitations of material selection becomes lesser because the materials will become more expensive as the factor of safety is greater. That means around 10. And if it is around 1, the material should be a cheaper type of material, okay, for the purpose, for the services purpose. And then if, let's say, for example, you go for a factor of safety of 9, then the material that you choose might be, okay, might be for greater jobs, okay, then the material should be very expensive, like titanium and all those things, okay. Now this is for ductile materials. I hope you understand. I hope you know what is ductile materials, what is brittle material. Ductile materials is materials such that when you apply force, it will undergo increase in length. When you remove force, the object can easily spring back. Okay, and then if the material fracture or it breaks, okay, it shows, okay, a fibrous, okay, fracture. It shows fibrous fracture. Okay. Now, very important property of a material. Okay, ductility is defined as the ability of the material to be drawn out into wire form. Okay, that means the ability of the material to be withdrawn out into very slim or wire form. That is for ductile materials. If non-ductile materials we call brittle. Okay, it cannot be stretched out in length. Okay, even though a slight increase in length, the material will break. That is brittle. And usually when you find out that when the material fails under brittle materials fail under tensile, it shows you crystalline and fracture. Okay, ductile materials will show you fibrous, okay, fracture. Now, a very important property of a material that can be measured in a tensile test is that of the ductility. Okay, I repeat once more, ductility is the ability of the material to be stretched out in length. I hope some of you have done the properties of material, okay? So actually properties of material is very important for you before you do this subject. Okay, so if you have done that subject, it is much more easier for you to understand what is ductile, brittles, and so on. Okay, a material is said to be ductile if it can be drawn out, that means stretched out, without fracturing. That means it can be stretched out into wire form, W-I-R-E, and is specified by the increase in gauge length. So to measure ductility, we measure the percentage elongation, one method. The second method is by measuring the percentage reduction in area. These two methods is used to measure, okay, the ductility of the material. So percentage elongation, you can take final length minus original length. That means that is the changes in length over original length, then times 100%. Okay. Now, if you use the percentage reduction area method, then you have original area minus area at fracture over original area. Okay, I hope you all understand what it meant. Okay, so these are the examples, but these examples, we will go to these examples later. in the later stage. Okay, so this section ends here. Okay, so we will continue with the next section afterward.